In previous videos, we have seen the syntax of the Lambda calculus, and we have also seen that the computational model of functional programming is equational reasoning. So here we want to bring these two things together. So remember that a lambda expression, lambda n.n plus 1, is our new way of writing the function that adds 1 to a formal parameter n. And if you write lambda n.n plus 1, 0, then we expect some kind of computation. Like, what do? We do 0 plus 1. And then 0 plus 1 is 1. So the task in front of us is really to justify the first of the two equations. So maybe just some terminology which we use in lambda calculus. So we also call an application of an equation here in the reasoning step a reduction. So the idea is that we always reason from the more complicated to the simpler side. That's the idea. And also we call the expression that gets reduced the red x. Right, so these are the radices that we reduce. So each reduction must be justified by a computation rule. And the second equation here is justified by our usual computation rules for arithmetic. And the question is now, what is the computation rule that allows us to take the step that lambda n.n plus 1 applied to 0 equals 0 plus 1. So if we look at this, it looks like simply we kind of replace the n by a 0. And then also it looks like we kind of erase some stuff here. So we kind of erase this and then this. And the n becomes the 0. So this rule is called the beta rule for historical reasons. So this is called the beta rule. And also sometimes you write a little beta down here to emphasize a reasoning step justified by the beta rule. And so what is the idea of the beta rule? So let me just formulate this. Explicitly. So the idea of the beta rule is that application is substitution. Application is substitution. So in our example, we substitute the 0 for the n. That's the idea. So let's look at how this plays out if we have a slightly more complicated example. So let's take, for a change, a function that takes 2 arguments. So we write this in lambda calculus as a function. Actually, I wanted to call them x and y now, the arguments. We write a function that takes 2 arguments in lambda calculus as a function which takes 1 argument and returns a function which takes another argument, and then that function is doing the actual computation. So all in all, this is a function that takes 2 arguments, and I want to apply this to the numbers 2 and 3. And now I want to use our new beta rule just to see like what is the computation that is happening here. So let's just quickly recall what the beta rule is. So we have a variable here, And this variable indicates a place in the body of the function. And so the beta rule tells us that everywhere we have x in the body of the function, we need to replace the x by its argument. So application is substitution. So what we need to do here is we need to substitute the 2 for the x. Okay, and then also this goes away. And okay, so and this also goes away. And the 2 goes away as well. So let's just write what we have. So we're left with a lambda y, and then now I need to be careful not to write x, but I need to write 2, and all the rest just is copied down from above. Okay, so this was the beta rule, and then I have another computation, and what I'm doing here is the same thing again. So I have a variable which I replace by the argument. So I just I don't need the parentheses here. So I just get 2 plus 3, and then I can use my computation rules for arithmetic and compute 5. Okay, so now we need to discuss one more interesting thing, and that is what makes the semantics of the lambda calculus both powerful and complicated. And so the question we want to discuss next is like, what happens if we do exactly the same thing, but now one of our arguments is also a variable. So let's do, I'm just copying this down. Actually, let us get used to using a bit less parentheses. So I want to write this down now as, drop some parentheses and write this just as lambda x, lambda y, x plus y. So this is my function, my addition function. And now I have a variable here, z, and let's keep it 3. So I can still do the same kind of computation, and it works in exactly the same way. So just where before I substitute 2 for x, I substitute now z for x. So I get lambda y dot z plus y, and then I get 3, and then I can still continue my computation, z plus 3. So now I cannot continue my computation because I don't know the value of z, right? So, well, let's say if I don't know the value of z, I cannot continue here. So on the other hand, the variables x and y are different, right? So x and y don't have values; they're just placeholders, and I don't need to know anything about x and y in order to do my computation steps here. So we are familiar with this idea from programming. So one are the x and y are the formal parameters in a function which I can freely rename, whereas the z is, you can think of it as a global variable maybe, or as an address, or as a channel. So we can't just replace z by some other value and think that it's the same program. So let's introduce some terminology here. So the z is a bound variable, whereas the x and the y, sorry, I just got this wrong. I just wanted to say it exactly the other way around. So x and y are the bound variables, and z is a free variable. Also, the lambda x and the lambda y are called the binders because they are making sure that x and y are actually bound variables. Okay, so what are bound variables? So bound variables are just placeholders. That's one way to think about them. And another thing is that they don't have values. On the other hand, a free variable means something outside, and it needs a value to finish computation. Needs a value here. We need here a value for z to finish the computation. Or at least, let's say, what do I mean by to finish the computation? I mean to evaluate to a number. So we need a value for z to, let's say to evaluate to a number. Maybe that's more precise. To evaluate to a number. So now something maybe surprising happens. Namely, we need another rule in order to allow for all computations we need to do. And this has to do with this distinction between free and bound variables. So remember that the bound variables here, the x and the y, are just placeholders. They're not visible on the outside. So the scope of the x is this, and the scope of the y is this. So everything to the right of the lambda. And outside of the scope, x and y are not known. X and y are not visible. So I should be allowed to put a y here instead of a z, right? So there should be no conflict between there should be no conflict between these two y's, because the one is bound, the other is free, and the bound y is not visible outside of its scope. So there should be no conflict. But let's see what happens if we do the computation following the same steps as above. So if I'm naive and I just copy what I have above, but with a y instead of a z, you see that I get y plus y here. And suddenly something is strange, because now if I replace the y by 3, I get 3 plus 3, and then this gives me 6. And before we just said, oh, we shouldn't be able to evaluate this expression without knowing the value of y. But here suddenly the y disappears. This looks wrong, right? So the y shouldn't be allowed to disappear somehow. So the question is here, what is wrong? So what is wrong here? Now, let's go through the reasoning steps. There are only 3 steps, so we should be able to find out what is wrong. So 3 plus 3 is 6. I think we can say that that is safe. And also, the middle equation looks like really solid, right? So I'm just applying the beta rule as I specified it. So what is wrong here must be this one then. And if you use our terminology about free and bound variables, you see what is wrong. So let me use a different color. So let me give a different color to the free variable. So now we see that we have 2 different y's. We have a blue y and a magenta y, right? And we substitute the magenta y for the x. So the magenta y goes here, and the magenta y was the free variable. So what shouldn't happen is that what we shouldn't allow is to let a blue y bind a magenta y. But in lambda calculus, obviously, we don't have colors. I just use the colors here in order to show exactly what's going wrong here, right? So the magenta y, which is just a y, gets bound by the blue y. So we call this the capture of a free variable. So the idea is to prohibit capture of free variables. So substitution is not allowed to capture variables. To capture free variables. That's the idea. So we modify the beta rule, which we have seen before, in such a way that we don't allow capture of free variables. But then this means that we need to add another rule to lambda calculus, to a semantics to lambda calculus. And the reason is that we still want to do our original computation, right? So if we have lambda x dot lambda y dot x plus y, and I apply this to y3, then I want still to be able to reduce this to y plus 3, right? Because whether the free variable is a y or a z, I mean, they may have different values, the y and the z, but in this part of the computation, I don't use the values of y and z. So this part of the computation should be the same for y and z. It shouldn't depend on the actual name. So, but at the moment, this computation is not possible because we restricted the beta rule. So we need a new rule to make this computation possible after all. And the idea here is the following. So x and y, the bound variables x and y, in particular the bound y, is just, as we said, a placeholder. And the name of placeholders doesn't matter. So what I can do is I can just replace the name of the placeholder by a different one. So I can replace here the y by a z. It's like in a C function, you can rename the parameters of your function without changing the function. So I just use a z here instead of a y, and it's really the same function, right? So this is important to understand here. And so we add a new rule, which is called the alpha rule, maybe not surprising. The other rule is the beta rule, then this rule is the alpha rule. And so we also say that these two expressions are alpha equivalent, and we really think of them as the same expression. And this is simply because for the functions, it doesn't matter if I rename the bound value, so these are really exactly the same expression. But now you see that even with my restricted beta rule, I can continue the computation, right? Because the y is now not captured anymore if I substitute the y for the x. So I can now substitute the y for the x, so I get a y here, and I keep the 3, and then again I can do my usual computation, and I end up with another beta step, with another beta reduction. I end up at, so what is the 3 is the z, right? So the 3 becomes the z, so y plus 3. Okay, so that's the semantics of the lambda calculus. There is not more than that. There's these two rules, alpha and beta. Alpha is renaming of bound variables, something you are very familiar with. And the beta rule is also something you're familiar with from programming, because that's essentially how you apply a function to an argument in C-like programming languages as well. So this is all we have in the so-called pure Lambda calculus. And we will see later how we can use this to understand better the semantics of programming languages in general. Thanks for watching.